So as I was saying, you should have those 4 handouts. The first one is the one that is sideways. It's not sideways up on my screen, but this one here that says the nature of friction. So what I did was, at one time I made kids make notes from this, and that didn't go over very well. People didn't like that. So I made some notes for you based on that. So if you feel that at the end of the notes you need to do a little bit more digging for some information, or if you don't quite get it, you want to read the extended version, it's there in that handout. Okay? Let me close it here. And I should be able to open it here. So you can consider these notes, if you will, but again, all of this comes from that reading. So if you wanted to sort of try and find it as you go through and highlight, if you want to do that as well, you can do that. However you think you need to prepare yourself for next week's final test. We're missing a few today, aren't we? Hopefully they get this information. So, yeah, the nature of friction, or here's where things start to get rough. Slight little smile from Ashley, and that's about it. Sarah's got a bigger smile. That's nice to see. All right, so let's begin. So friction is, we've talked about friction before, but I'm going to sort of jump in a little bit deeper and give you some more information about friction. It's a force that resists motion, and it involves objects that are in contact with each other. There must be contact. It is a contact force. Friction can be considered to be air resistance as well. So something flies through the air, it's in contact with the molecules that make up the atmosphere, right? So some cause of friction. There's still some debate on this, on the idea of friction. They believe that an object deforms a surface and vice versa. So in other words, if I put like a laptop here on a table, they're saying that it actually makes a little sort of depression, if you will, in the table kind of thing. So it kind of looks like this, right? There's my laptop, right? Here's the table. So they're saying that it actually does that. Now I've exaggerated it significantly to see it, right? And so then they believe that a plowing force is required to move the object over these deformations. Or you're in fact kind of going uphill, slightly uphill. There's some debate around that. Irregularities interlock and offer resistance to the movement. So that what they're talking about there is that the table itself is not exactly smooth, right? And so these little sort of humps and bumps kind of lock together and create resistance. When you're down in the carpentry, in the wood shop, and you use sandpaper, what are you doing? Like, what does the wood feel like after you sand it? Smoother. How come? Because you're taking off the hills, I guess, right? The high points. What does the sandpaper feel like after you're done? Usually smoother as well, right? So you're literally taking off bits and pieces. Now, having said that, something that's really like a tabletop is fairly smooth, right? But like something like this, a basket on a tabletop obviously slows down significantly, doesn't it? Right? How smooth is the basket? Well, it's fairly rough. Let's find something a little smoother. Kind of sticky. Let's try this. This is kind of like a curling rock. How come? Because there's just sort of like a, what do they call it in curling? What do they call that? What do they call it, like the gliding surface or something like that, right? That goes a little farther, right? But there's still a significant amount of friction. Hey, Lane, when you spin a curling rock, go over here. I'll do it because I know how hard to push. I don't want to, But I showed this to my grade 12s the other day. If I spin a curling rock, like if I want it to go this way, right? If I want it to go that way, which way would I spin it? I'd spin it that way? Okay, so let's see if it does that here. Good that you weren't doing that, right? Good in hand. Let's do it on the floor. So if I want it to go this way, I spin it that way, right? I was so good at it yesterday.
Well, it was yesterday.
I know, yesterday was yesterday, right? You're only as good as your last rock. Where did it go? Did it? No, you're watching very close.
I was watching the movie.
It went, did it not go the other way? Did it not go left? Which way did it go, Colby?
It went this way, it went this way, and then it did a circle and went.
Really?
And then I watched the video. See, look, it always came back. Because it spins. It goes this way, and then it goes back this way.
But it kept spinning this way, did it not? Like, the spin was the same. It literally, I don't think it went this way. It went like this, and then right at the very end, it went like this, didn't it? That's not how acrylic rock behaves, is it? You know why? Yeah, why does it do like acrylic rock?
Because it's a cup.
It's not ice. It's not ice? That's the number one. Because when it's sliding, acrylic rock actually is sliding, because of the friction, it actually heats up and it becomes water. And then you're talking about some fluid dynamics as well, just like this stuff. Good job. Boy, you guys that aren't here sure missed a great demonstration. Talking to the people that are going to watch this.
Nobody watches. How do you know?
Really? Nobody watches this? Well, I don't look because it makes me feel bad. Okay, you should know these two things. Starting friction and sliding friction. It'll be in that handout there. So starting friction is the maximum frictional force between stationary objects. So maximum implies that it is the biggest, right? And sliding friction is the frictional force between objects that are sliding with respect to each other. Now the other word for starting friction is static. And the other word for sliding friction is kinetic. Starting friction or static is always greater than, but sometimes equal to, kinetic. Kinetic means that it's moving. Okay? Up to now, all I've done is said the friction force is 4 newtons or something like that, right? We're going to peel that back a little bit and look a little bit more closely. I'll pause there. Okay, some properties or characteristics of friction. If you find that in your reading there, I think it's on the second page. Anyone see it there where it says properties of friction? So it's pretty much right on that. So I'll just sort of summarize that. Friction acts parallel to the surfaces that are in contact and in the direction opposite to the motion of the object or to the net force tending to produce such motion. So when I push the coffee cup on the table, right, the motion is that way, friction is opposite the motion. If I push on the coffee cup but I don't push very hard, right, friction is still opposite that push. Even though it's not moving, friction is opposite the motion that's trying to make that motion. Friction depends on the nature of the materials in contact and the smoothness of their surfaces. How smooth they are depends on, or is the determining factor. Now, there's actually some talk about you can get things so smooth that they actually increase friction. Why do you think that might be? How could you get like two surfaces? Think about like glass on glass. What would be the friction? Like how easy would glass slide on glass? It'd be like a suction kind of thing. You're absolutely right. There's that sort of vacuum of the air pressure. So there is some talk that you can get it so smooth that you actually increase friction. And there's also talk that they're so smooth that they're so close together on a microscopic level that you've actually got intermolecular forces attracting. But for the most part, smoother things have less friction. Sliding friction is less than or equal to starting friction. I think I said that already, right? Less than or equal to. Static is greater than or equal to kinetic. Friction is practically independent of the area of contact. Now, how I usually explain that? I usually get a book. So for those of you that are watching at home, and you're all going to, okay, if I've got a book here and it's just sort of sitting on a table like regular, and it's got a certain amount of friction, right? As I push it, it slows down, obviously. What if I put it on its spine, on its back like that? Much smaller surface area. How much friction is there? Friction is practically independent of the area of contact. In other words, there's just as much friction when it's sliding on its back as there is on its spine, I guess, as compared to its back. Provided that this is the same surface as this. Like if this was made out of sandpaper, obviously that would be different, right? But yes, the friction is independent. A lot of people are confused by that. What about the pressure? What's the difference between pressure here on the spine and pressure there? Exactly. It's like going on thin ice, right? You spread yourself out, you reduce the pressure, you reduce the force. But here, the friction is the same. Feel any better? You feel any better? No? You'll let me know if it gets worse? Okay. Thank you, Meg. And the last one, starting or sliding friction is directly proportional to the force pressing the two surfaces together, right? So if I've got an object sliding, if I put a weight on there, if I say put my hole punch on top of the book, does that increase the gravitational force down? Will it slide as far? Right? People will say it's because it's bigger, but it's also got to do with the friction. More weight, more force, right? If I put something on top, more weight, more force, more weight, force, more friction. Now, here's something you've never seen before. You need to write that down. Even if you haven't written a thing down, you need to write this one down. Okay? It's called the coefficient of sliding friction. Coefficient of sliding friction. It is the ratio of the force of sliding friction to the normal force. And this is how you write it. That funny-looking Greek letter is the Greek letter mu. When you write it like that, it's a U with sort of a tail on the front. It's the Greek version of the letter M. M is used for slope. Here's a question though, Vinny. What do Greek kids use? Do they use Greek letters or reuse Greek letters? Or do they use English letters or reuse Greek letters? I don't know. We just use Greek letters because that's sort of where science sort of first originated. When I was in Greece about no, even more than that, maybe 7 or 8 years ago, I really wanted to know this answer, so I looked for teenagers to ask them, but my wife wouldn't let me. She thought it was weird.
That's kind of weird. I'd be weird about the guys saying, hey, what kind of life do you want?
It is kind of, in hindsight, it is kind of weird, but I still would like to know. Well, good thing that there was no creepy old guy with me when I was there. Mu is FF over Fm. What does FF stand for? Friction force. And Fn stands for normal force. Right? So that is a formula that you will need to be able to use. Mu equals FF over Fn, and you'll be using it in grade 12 as well. It's fairly important. Anytime there's any friction, you're going to use it. Okay? So put that in your little toolbox of formulas. Do you have a page with example questions on it? Yep. Excellent. Let's move to that one. Move to the page with example questions. I think, do you have how many? Oh, we got 3. Okay. So we got quite a few. All right, so you've sort of been given the kind of the background theory here on friction. Let's look into sort of more of the math. A box with a mass of 175 kilograms hold along a level floor with a constant velocity. Now, constant velocity is important. Why is that important? What does that mean? If the velocity is constant, The forces are equal, balanced. Net force is 0. If the coefficient of friction between the box and the floor is 0.34, what horizontal force is exerted in pulling the box? I should go back to here for a second. And I'm going to write almost always less than 1. The coefficient of friction is almost always less than 1. Very rarely will it be more than 1. Okay, so you're usually going to get numbers like 0.2, 0.3, and so on. In grade 12, we do an experiment, and we actually determine the coefficient of friction wood on wood. It's less than 1. Okay, so let's just reread this here. We got a box with a mass of 175 kilograms. So that means that the M value is 175, right? Pulled along a level floor, and so no ramp. You're going to see nothing but level floors. Constant velocity, that means our forces are balanced. If the coefficient of friction between the box and the floor is 0.34, so that is our mu value, what horizontal force is exerted in pulling the box? What horizontal force is exerted? So we're asked to find the FA, the applied force. How much force is being applied? Right? What horizontal force is exerted? Is applied. Okay, should we draw a little FBD, a little free body diagram?
Sure.
We probably should, right? Okay, so it's on Earth, so we got weight force. Is the FF equal to the FN? Are the vertical forces balanced? It's not accelerating that way, so it should be. So now we've got an FA this way, and we've got an FF. Are those balanced? Are they equal?
Yeah.
And the answer is yes, because it's a constant velocity. So what horizontal force is applied? So FA, if I can get my FF, that'll tell me my FA, right? And FF is in that new formula that I just came up with. I know the mu value, I don't know the FN. Can I get the FN from the FW? Yep, because they're equal to each other, and I know I can always get FW, so that's where I'm going to start. Did you see how I kind of gave you a roadmap? FW is equal to mg. Did you see how I kind of thought that through? Work backwards. The mass, 175. G minus 9.8. Sorry, 1715. Negative 1715. So the weight force is minus 1715. What's the normal force? Well, it's just the positive version of that, right? For the time being, you might want to start showing, you might want to show that value. Many of you will sort of figure that out. That's always going to be the case. And we can just sort of leave it. We don't have to actually describe it. Okay, so now I've got to find my FF, right? That was the next thing. So I'm going to go mu equals FF over Fn. The mu value is 0.34. We're solving for FF. The Fn is 1715. Okay, and I'm reminded that you got to be able to solve this kind of stuff. That's just a multiply. So I've still got that number here in my calculator. So I take that 715 or 1715, and I'm just going to multiply by 0.34. 583.1. That's the friction force, 583.1. But I need to know the applied force. But we said they're equal to each other, right? I showed you guys the 3 dots, right?
Yeah.
Therefore, the applied force is 583.1. The applied force is 583.1 newtons. Now, I notice here, let me just think out loud here for a second. I notice that these numbers are the same, but these forces are opposite. Like, shouldn't one be positive and shouldn't one be negative? Which one should be negative here? The friction force should be negative. But notice that it doesn't come out of the formula negative. Okay? You have to actually sort of make it negative. Because all it really means is to the left, right? But it doesn't come out of the formula as negative because, well, the Fn is positive, but that's because it's positive up, right? Positive up and positive right are two different things. So you do have to manually sort of put it in there. Most classes usually ask me, what are the units for mu? And no one asked me that today. So I'm going to ask the question, what are the units for mu? Newtons? That's usually the answer. Well, what is the unit for friction? Or for friction force? Newtons, right? And what is the unit for normal force? Newtons. And when you've got newtons over newtons, what happens? They cancel. There is no units for mu. Mu is a ratio. It has no units. Okay? But having said that, applied forces do have units. So really, there's a lot of reading there, but really this question is just 2 steps. Really. Think they get harder? Of course they do. You'd be wrong, Paul. How can I make it a little bit harder? Well, instead of the force being balanced, I could make there be a overall acceleration. So let's look at this example then. A box with a mass of 100 kilograms is accelerated by a force of 200 newtons across a level floor. Again, level floor. If the coefficient of friction between the box and the floor is 0.2, what is the overall acceleration of the box? So virtually the same situation, except the applied force is much, much bigger. Weight force, normal force. Friction, applied force. Why is the applied force so much bigger? It's accelerating. So this value here is 200. The friction force then should be, to make it all work out, the friction force should be something less than 200, right? Are we going to kind of do the same steps, do you think? I have to find the overall acceleration. What do I need to know before I can get the overall acceleration? I know the mass. I need to find the net force. Before I got to find the net force. Before that, I got to find the friction. Right? You can almost always begin these finding the weight force, Fw, mass times gravity. 100 minus 9.8 minus 980 newtons is the weight force. Minus 980. I didn't write that very good. Therefore, normal force 980. Up. I got my mu, I can find my friction force, right? Same step as before. Ff over Fn. This time it's 0.20. Solve for friction. 980. You're multiplying, right? .2 times 980. $196. Oh, that's quite a bit. The applied force is 200. Is it still more? Probably a little bit. So now what? See how I'm kind of building here, making it a little bit harder? Now I'm going to say F net is equal to FA plus FF. Remember that the net force simply means the sum of all the forces, add them all up. Applied force 200. Let's put plus minus 196. Squeeze it in. Or just move it over, might be better. So the F net is only 4, right? 200 minus 196. The net force is 4. Okay, Anna? You look concerned. Oh, okay. F net is equal to ma. The net force is 4. The mass was it 100? Yep. Gonna divide. 4 divided by 100. 0.04. Now what do we measure acceleration in? Meters per second squared. So that's a few more steps. That's 4 steps altogether. Make sense? Yeah? No, Anna? Need some time to process?
Yeah.
Okay. Okay. One more to go, I think, right? Okay. I'm going to let you read it on your own. You read for a second, then I'll read. You read it. Here we go, another box. Mass 46 kilograms. Pulled along a level floor at a constant speed by a rope that makes an angle of 30 degrees. So now I've got this problem. Have we done ones like that yet before? I think we have, right? What do we call that sideways bit? Yeah, we've done that before. We're calling that FAX, right? The X component of FA. If the force on the rope is 260 newtons, what is the horizontal component? Here I've got FH, because that's what I used to call it, FAX. What is the normal force, and what is the coefficient of sliding friction? Okay, well this doesn't look too bad. This just looks like the same kind of question, just a little bit, sort of one more layer, right? Just going to put it on the next page here. The mass is 46 kilograms. So the first step would be to find the weight force. M times G, what was it, 46? 46 times minus 9.8. And it looks like I've already worked it out. It's minus 450.8. Doesn't have a negative sign in there. But that's the same as my Fn. 450.8. Oh, no, hold on. If there's an FAX, a horizontal component, is there an FAY that lifts up? Like, you think about that. If you're pulling on a rope, you're pulling on something at an angle, sideways, yeah, you're pulling at an angle, it's coming sideways, but isn't it also lifting it up as well? The answer to that is, of course. There is, if you go back to the diagram, there is this thing here, and I think I had briefly alluded to it in the last unit, FAY. There is a Y component. There is a force that is up. And what does that do to the value of Fn? Does it have any effect on that? Mallory's saying yes, it does. Does it make it bigger or make it smaller, Mallory? You know? I'm not sure yet. Would you agree that all of the Y forces have to be balanced? Because it's not accelerating up and down, right? Okay, here's where things get a fair bit more complicated right away. But first of all, part A, what is the horizontal component? So all we really have to do, I guess, part A, is find my FAX, which we know to be FA cos theta. We learned that last unit. FA cos theta. So 260 cosine 30 degrees. Good thing you guys are here today. This is tough stuff. 260 times 30 cos, 225. So of the 260, 225 is pulling sideways. But there's a little bit up as well. Right? There's this bit here, FAY. Now if FAX is FA cos theta, because cos is adjacent, FAY is going to be what? It's going to be FA sine theta. How come sine? Because it's opposite. Is FAY always going to be the sine? almost always. So 260 times the sine of 30. 130 newtons. 130 newtons of your applied force is actually lifting it up. If you're trying to push a heavy object across the floor, does lifting it help as you push? It does. How come, Colby? Less friction. You are, in fact, reducing the friction. I'm going to explain why. Because that FAY is reducing the normal force. So now, if I'm going to redraw my diagram here. I've got weight force down, I've got normal force up, and I've got FAY up. I got two forces up, one down, and the one that matters to friction is the Fn. So the sum of those has to be 0. Why does the sum of them have to be 0? Because it's not accelerating up and down, right? So here's where kids start to get freaked out a little bit. So just let me write this down, then I'll explain. I'm going to write F net Y is equal to FW plus Fn plus FAY. I'll say that again. Alana, you should really watch this. This is the hardest thing we've done all year, and you're busy texting. That's not going to help your mark. F net Y, the sum of all the Y forces up and down, is equal to all the Y up and down forces, which are FW, Fn, and FAY. And F net Y has to be equal to 0. Why? Why 0? It's overall balance. It's not accelerating up or down. You're right, Trent. And the FW we've already figured out to be minus 450.8. This is wrong up here. Minus 450.8. I don't know my Fn. That's what I want to know. And my FAY is this value here. Now, what direction is FAY? It's up, so it's going to be positive. Does it matter that positive and negative here? Huge. It matters. Okay, you got to get it right. The FW is definitely down. So now I got to solve for Fn, right? Let's leave the Fn over here. Minus 450.8 goes to the other side and becomes plus 450.8. And the 130 goes to the other side and becomes minus 130. And that's because the normal force is reduced by that FAY. I'm going to subtract it. The Fn is actually 320.8. Now, as Colby pointed out, you reduce friction when you lift up because you're helping out the normal force. It doesn't have to work as hard. I'm reducing friction. I'm almost done. Okay? So, if I just go back, I'll come back to this page right away. Back here, right, the FW and the Fn were equal to each other. That's because those are the only two Y forces. Now I have a Y force, so my Fn is less here. Okay, so what was the actual question? What is the normal force? So that's B. So this whole thing is, all of this is B. That's A, all this is B. And part C asks, what is the coefficient of sliding friction? Mu equals FF over Fn. Well, I just solved for Fn. Do I have a friction force? Do I have a left-right friction? I don't see one here. In fact, I don't even have, I got FF there, but, well, is it moving at a constant speed? It is, and so that means that the FF, all of the XY forces have to be equal to each other, balanced. The FF has to equal the FAX, because there is no net force left and right. The FF is equal to the FAX. So you could hopefully fill that in there. Therefore, FF is equal to minus 225. So now it's a simple matter here. Now, do I put the negative in my mu formula? I don't. Okay, mu is just a ratio. It's not really a vector thing. They don't care what direction. So the FF is 225. And my Fn is this new value here, 320.8. 225 divided by 320.8. 0.7. 0.70. Does that seem like a reasonable value? I've told you that the mu values should always be less than 1, so yes. We went from relatively simple to relatively hard in 3 steps. Think back to where you were in September. If I'd shown you that in September, would you have walked for the door? Said, forget it, I'm not sticking around for this nonsense. Probably. So you must have learned something along the way. Okay, time for me to be quiet. You have, in your handouts there, you have a couple of packages of stuff. On the sideways one, there are a few problems here on the sideways one. There are answers and a solution code there. Then I gave you 2 more. There's extra friction gravitational fields questions part 1. There's a whole whack there with answers and a QR code. And then there's even more because I have them, so I figured I'm out to get them. But you get lots that you can practice over the weekend. We're still aiming for, the more I think about this, the more I think we should aim for Thursday. Yeah. Let's plan for the test being on Thursday.